Hello, my name is Sean, and I'm going to do the tour of the universe. Zooming out, we see a sun and a planet. There are 8 planets split up into 2 groups, terrestrial and gas giants. The 4 terrestrial planets are Mercury, Venus, Earth, Mars, and the gas giants are Jupiter, Saturn, Uranus, Neptune, and there are also various dwarf planets. Going across the screen now.
This is the solar system as a whole. Right here in the middle, you will see the asteroid belt. Now at the end here, you will see the Kuiper belt. This is our Milky Way.
That's the galaxy we all live on. And now we're going to be panning right to its neighbor, Andromeda, the closest galaxy to us right now. Alright, that was a lot of information, so we're going to take a little breather here. We're going to stop for a second, and we're going to talk about how planets are formed. So you take two balls, and then you combine them. And then just like this animation will play, when they combine, debris shoots off from the collision point, and it makes the moon. Alright, so yeah, that's a pretty cool animation, huh? So let's press the pause button here. These are going around in a circle because of gravity. Now let's talk about gravity for a second. So imagine a table with a cloth on it. So this cloth represents the gravitational plane. Now imagine you put a heavy metal ball in it representing the sun, and then you rolled a small ball across the plane. This would represent the planet orbiting. In the real world, it would fall down because of Earth's gravitational pull, but in space, Earth's gravitational pull does not exist, so it would just keep circling around forever. Alright, let's talk for a second about the Big Bang Theory. So it was named by some guy making fun of the name, but it eventually stuck. He mockingly called it Big Bang. So that's an atom for scale, and that's literally everything in the universe. But then eventually some big ol' explosion happened, and that is not fire. Fire can't exist in space, but that is a big explosion that happened. It was massive, and everything spread out all over the universe. There are 2 big problems with this theory that scientists haven't figured out yet. So how to get there is the first one. Like, we don't know how it got there. And the second one is how did it explode? How did it, go all over? And we don't know what happened. Alright, so scientists have been thinking about these questions for years. But they actually do have some proof, like the redshift and Doppler effect, which proves that stars are moving away from us, which therefore suggests a starting point for the universe. Alright, so these questions are the reason that the Big Bang Theory isn't a law. The life cycle of a star. So you start with a nebula, right? And then it becomes a protostar. And then it becomes a main sequence star. This is the main sequence that our sun is in right now. It's when it combines hydrogen into helium, which is the next element. So then after main sequence, the next phase depends on the mass of the sun. If it's 1.5 times or more the mass of the sun, it becomes a red supergiant. And after that, once it begins to fuse elements higher than iron, it becomes a supernova. And then after that, it either becomes a neutron star or a black hole. And then after that, the supernova can become a nebula again, and a protostar can form. Let's go over to the red giant, which forms if the sun is 1.5 times or less the mass of the sun. After that, it becomes a red giant, and then eventually it will begin to fuse elements higher than iron again and become a white dwarf. And then eventually it loses its energy and becomes a black dwarf. But then this poses the question, how do scientists know what stage a star is in? Well, scientists figure this out by examining what kind of elements are on the sun. So, for example, a main sequence star would have helium and hydrogen, but a red giant would have carbon, magnesium, and iron, for example. But how is this crucial to life? Well, our sun is perfect for our Earth because the protostar would be far too dim and cold for the Earth, and a red giant would be far too big and hot for the Earth. Well, touched on this briefly, but after a supernova happens, then a nebula can form and protostars can form from that. Now let's talk about waves. This here is a transverse wave. So let's talk about the crest and the trough. The crest is the high point of the wave, and the trough is the low point. The wavelength is the distance between 2 points on the wave. So, for example, that wouldn't be the wavelength. And finally, the amplitude is the distance from the baseline to the crest or the baseline to the trough. That would not be the amplitude, for example. Let's talk about longitudinal waves. Longitudinal waves are made up of compressions and rarefactions. Compressions are where they get close together, and rarefactions are when they get far apart. The wavelength, just like in the previous wave, is the distance between 2 points on the wave. For example, the distance between the first particle in one rarefaction, the first particle in another. The amplitude is a bit tricky. It can be defined as the distance between two particles in a compression, but it can also be two particles in a rarefaction. It's pretty much how extreme the difference is. Let's look at some examples to illustrate my point. The first example I have for you is a high amplitude short wavelength. It's high amplitude because the distance between compressions are very short. It's a short wavelength because the wavelength is short. Simple enough. It's a bit tricky with the amplitude because it works in reverse. The shorter the amplitude is, the higher it is, and the longer, the lower the amplitude. The next example is a high amplitude long wavelength. The wavelength is very long in that picture. And it's a high amplitude because the distance between two particles in that compression are very, very short. In sound waves, this would translate to a very loud, low sound. Low because of the long wavelength, and loud because of the high amplitude. Got one last example for you. It's a low amplitude short wavelength. The wavelength is short, and the amplitude is low because it's a relatively longer distance between those two particles in the compression. In sound waves, this would translate to a very quiet, low sound. Now let's talk about energy in waves. So energy in waves is very simple. As the energy increases in a wave, the amplitude increases, and as the amplitude increases, the energy increases. So in sound, because it's the easiest example, if you have a sound wave with a lot of energy, the amplitude would be very high, and if the amplitude's high, then the energy is high. Let's talk about frequency. The frequency is also pretty simple. A frequency is just how many cycles it can complete in a minute, which would mean that a long wavelength is a short frequency, and a short wavelength is a high frequency. It's pretty easy. Just like the energy, it's just sort of a simple pattern like this. Alright, next we're going to talk a little bit about gravity. Now, gravity is very important to human life. In the Big Bang Theory, it's what supposedly held all matter together. And I touched on this briefly earlier, but it's like that model of everything spinning around a heavy ball on a cloth. It's what keeps galaxies together, it's what holds them together, and it's what keeps you on the ground. If it wasn't for it, you'd simply fly off. And it is completely essential to human life as we know it. Alright, you're almost done. The last thing we need to talk about is the moon. Now, the moon is very essential to human life. As this diagram says, it rotates in a period of 28 days, and here is every phase of the moon. So for this one on the left, the sun is hitting it, and it's facing away from us, therefore we can't see anything. This would be the new moon, where we can't see the moon at all. And then the one on the right is where the sun is hitting it directly again, but this time we can see it. It is bright, and this would be a full moon. And there are phases in between that, which I will list now. So here are the phases of the moon in order. You got the new moon, you got the waxing crescent, you got the first quarter, the waxing gibbous, then you got the full moon, which is where we can see all of it, the waning gibbous, the third quarter, the waxing crescent, and then a new moon again, where we can't see anything. The sun is hitting it away from us. Now, again, this goes in a cycle of 28 days, which is where we get our month. And now for eclipses. We all like eclipses. Eclipse means when one thing is going over another thing. So here the sun's hitting the moon, casting a shadow on the earth. That's the penumbra and umbra. And the lunar eclipse is the opposite, where the earth is casting a shadow on the moon. There's the umbra and penumbra again. And that is it. Thank you guys for watching. I appreciate it. And yeah, I worked hard on this video, so I really hope you enjoyed it. I hope I got all my information across well enough. It took about 2 weeks to make. Well, thank you.